Alright, welcome back. And before we get going on some examples, I just want to clarify what I mean by the mole road. I mean, I mentioned it a few times, but I never really explained what it is. And really, it's just a way to help you understand these these conversions right here. And this one too. So let me just explain to you what I mean by that. So the mole road. This is the actual mole road. So we have liters, moles, grams, and atoms. Or I should say number of atoms. So when we're given moles, there's normally three things where we can find from that. That's liters, grams, or the number of atoms. If we're given moles and we want to find the number of liters, we want to go from moles to liters, then, like we said up here, there's just 22.4 liters per mole. 22.4 liters per 1 mole. So when we have 1 mole of a substance, that will occupy a space of 22.4 liters. When we want to go from moles to grams, like we said back up here, we have to look at the periodic table of elements. We have to look at the periodic table of elements to see the number, right? I think I still have it up right here, to see the number right under the elemental symbol. So from there, I'll just write periodic, well, it'll be the periodic table of elements value, that one value I just showed you, per 1 mole. And this value will change for all the elements. Now say we want to go from, we're given moles, some number of moles, and we want to figure out how many moles are, or how many atoms, how many individual atoms will make up that 1 mole. And as we said up here, we just have to look at Avogadro's number, because there's 6.022 times 10 to the 23rd atoms per 1 mole. We can just put that right here. 6.022 times 10 to the 23rd atoms per 1 mole. And I'll put grams here because I forgot to do that. This is the unit we use to describe all these values right here, these decimal place values. Okay, so with that being said, now we'll move on to some examples, keeping this in mind. I mean, by no means do you actually need this. You just need these conversion values up here. But the mole road is a nice way to help you remember what you need to know. Okay, so we'll put this into application right now. Example 1. We'll say you're given 2.3 moles of boron, the element boron. How many liters are there in the substance? Liters. Actually, we'll just write it out. How many liters are in the substance? How many grams are in the substance? And how many atoms are in the substance? So we're trying to find three things: liters, grams, and atoms from 2.3 moles of boron. So we have this given substance of boron, and we just need to convert it. We need to see how many moles will be equivalent to, or how many liters will be equivalent to 2.3 moles. Okay, so as we set up here, when we go from moles to liters, we know that there are 22.4 liters per 1 mole. Since we know that, and since we know we have 2.3 moles, we can just multiply the two numbers together. So 2.3 moles, and we know that per 1 mole there are 22.4 liters. We can just multiply these together, right? 22.4 times 2.3 moles. right? Because we have, it's simple multiplication. If we have 2 candies, or say we have 2 jars, as this is a small analogy, and each jar holds 3 candies, so to find the total amount of candy, we just multiply the number of jars times the number of candies. It's the same concept here. We have 2.3 moles, and each mole has 22.4 liters, so we can just multiply these together. Let me get my calculator here. 2.3 times 22.4, and that'll be equal to 51.52 liters of boron. So 2.3 moles of boron will occupy a volume of 51.52 liters of boron. Oop, that's the bottom of the space right there. We'll move to the right a bit. Okay, so next we are asked to find grams right here. So 2.3 moles of boron, 2 grams. And another thing I want to point out is, actually I'll point out after that. It'll be clear after I do grams what we can observe from the liters. So how did we find out how to get to grams? Well, we can look at the mole road here. When we're given moles and we're asked to go to grams, we have to use the periodic table of elements to find the number of grams per mole. And we said we were given boron, and boron is right here, and there are 10.8 grams per mole, right? Because that's what this number is. Carbon has 12 grams per mole. Nitrogen has 14 grams per mole. But we're asked to find boron, which is 10.8 grams per mole. 10.8 grams per 1 mole. Remember, we have 2.3 moles. So all we have to do again is just multiply these two numbers together, right? Because it's like having 2.3 jars full of 10.8 candy. To find the amount of candy, we just multiply them together. So 2.3 moles times 10.8 grams. And so that will just be equal to, let me get my calculator out, 2.3 times 10.8. That's equal to 24.84 grams of boron. Right? So when we're given this amount of moles, it's just the same. The 2.3 moles is the exact same thing as having 24.8 grams. We're just using two different units to describe it. It's like if we have 1 foot, it's the same thing as saying 12 inches. We're just describing it with two different units. But these two values, these two lengths, are the exact same. So 2.3 moles is actually the exact same thing as 24.84 grams. We're just using two different units to describe it. And what I wanted to point out before was, when we go from moles to liters, you can see that we didn't even use the periodic table of elements. We didn't use any values from it. We just used this standard 22.4 liters. So this shows us that when we have 2.3 moles of any substance, of any element, we'll always have 51.52 liters of that substance. This could have been 2.3 moles of carbon, or 2.3 moles of hydrogen, or 2.3 moles of oxygen. It could have been any one of these values, and we would have still been left with 51.52 liters of that element, because this is just the constant value for any element. For any 1 mole of any element, it'll give us 22.4 liters per moles we have. Okay, so our last one is we need to find the amount of atoms in 2.3 moles of boron. So we'll go up here a bit. We have 2.3 moles of boron, and we want to go to the number of atoms. And if we look over here at our mole road, when we go from moles to atoms, we know that there are 6.022 times 10 to the 23rd atoms per 1 mole. So we can use that over here. 2.3 multiplied by 6.022 times 10 to the 23rd, which remember is a huge number. So 6.02 times 10 to the 23rd atoms. This is moles. Remember, this is per 1 mole. And that is equal to, let me just get my calculator, this is a huge number, times 6.022 times 10 to the power of 23rd. That is equal to, this is equal to 1.385 times 10 to the power of 24. So that's the number, let me change colors here. Excuse me. So that's 1385 with 24 zeros after it. 1, 2, 3, 4, 5, 6, 7. As I said before, this is a huge number, all the way up to 24. But we can just represent this huge number of atoms. This is of atoms, by the way. 1.385 times 10 to the 24th atoms. This is the same thing as having 2.3 moles of that substance, which in this case was boron. But as you can see again, 2.3 moles, since we didn't even use any values of the periodic table of elements, this value is the same for all elements. We can see that this 2.3 moles of any substance, it could have been 2.3 moles of carbon or 2.3 moles of manganese or aluminum, it would have given us 1.385 times 10 to the 24th atoms. So another thing I wanted to point out was that, so we found the number of atoms right here. We found the number of grams, and we found the number of liters right here. And there's one thing I want to point out is that this number of liters of boron gives us this weight in grams of boron. So really 51.52 liters of boron is the same thing as 24.84 grams of boron. We're just using two different liters. We're just using the gram here and the liter here. And both of those are equivalent to 1.385 times 10 to the 24th atoms of boron. So when you have this many atoms of boron, it'll weigh exactly 24.84 grams of boron, which will those will occupy a space of 51.52 liters. So that's just another thing to think about when you're doing all this, is you're not really finding new numbers. Well, you are, but you're just finding new ways to express the number you're given.